Optimal in-place compaction of sliding cubes. Modular robots hold the promise to always have the right tool at hand. They are built from many small modules and can transform quickly from any shape to any other shape. One popular algorithmic model for modular robots is called sliding cubes. In this model, the robot is a phase-connected configuration of cube-shaped modules. The robot can transform its shape by performing a sequence of moves, one at a time. There are two different types of moves: slides and convex transitions. The robot always needs to stay phase-connected. So any move that would disconnect the robot, even temporarily, is forbidden. To transform a robot from one configuration to another, one common approach is to use an intermediate canonical configuration. We choose a compact configuration that packs the cubes tightly at the origin of the grid. That is, a configuration is compact if for any cube C, the entire cuboid of cubes spanning C and the origin is completely filled. To transform from a configuration A to a configuration B, we first compact both A and B towards the origin individually. It is straightforward to transform between two compacted configurations. For the complete transformation sequence, we first run the compaction sequence for configuration A, then we transform the compacted form of A into the compacted form of B, and finally we run the inverse compaction sequence for configuration B. So the only difficult part is how to compute a compaction sequence. In this video, we are going to explain our algorithm that can compact any configuration. In places, we will simplify the explanation for clarity, and we refer to the accompanying paper for the full details. To start off, consider this configuration. We call a set of vertically connected cubes a pillar. We say that a pillar is a cut pillar if its removal disconnects the configuration. Our first goal is to reduce the z-coordinates of cubes in non-cut pillars. This means that whenever we can move a cube downwards with either a slide or with a convex transition, we do so. Let's analyze what our configuration looks like, assuming that we cannot do any such moves anymore in a non-cut pillar P. Assume that P does not yet reach the ground. Let P' be a pillar next to P. On the bottom, P' cannot stick out below P because then we could have done this move. This holds for all pillars next to P. So any non-cut pillar is hanging off of other cubes and we cannot locally move its cubes downwards anymore. On such hanging pillars, we do an operation that we call a pillar shove. It takes a non-cut pillar, like P, folds half of it upwards and moves it aside, like this. At the end of the pillar shove, we make progress by moving the original top cube of P all the way down. This entire process takes a number of moves quadratic in the length of P. So if P is long, this would take many moves. In this case, we take a different approach that uses only a linear number of moves. We use the bottom cubes of P to create a zipper. It slides upwards over P, moving cubes of P to their new location one by one. Once the zipper reaches the top, P has been moved to the side in its entirety, after which we clean up the zipper. After doing all available pillar shoves, we can show that all non-cut pillars stand on the ground. We perform any remaining moves that move cubes in the -x or the -y direction. Now we still have to deal with the cut pillars. To do so, we work on low components, connected components in the ground layer. Take a non-cut low component L. L is connected to a cut pillar that we call a clearing pillar. We would like to do a pillar shove on the clearing pillar. However, we cannot do that as constructing the zipper would disconnect the pillar from L. Therefore, instead of gathering the cubes for the zipper from the pillar itself, we gather them from L. Then we can perform the pillar shove as before. The moves we presented so far always compact any input configuration. We want to use, at most, all sum of coordinates moves. This is quite a natural bound because if any individual cube at x, y, z wants to move to the origin, it needs to spend at least x plus y plus z moves. For this bound to hold, whenever we spend k moves, the sum of coordinates needs to be reduced by omega k. This is true for all operations except for the clearing pillar shoves. Gathering cubes from L can take a number of moves linear in the size of L. So if L is large, we need to avoid gathering cubes from L. But in this case, instead of doing a clearing pillar shove, we can find a move sequence that reconfigures L to contain the origin. To find this sequence, we execute our entire algorithm in 2D on the cubes of L. This is possible because, as it turns out, all of our operations only require 2 dimensions, so the algorithm works in 2D just fine. We need to avoid moving the cube beneath the clearing pillar, since that would break the configuration. However, we can show that moving this cube is never necessary. As soon as all low components reach the origin, they combine into a single low component. These moves together reconfigure any configuration into a compact configuration. The algorithm requires only O sum of coordinates moves, which is asymptotically optimal. Moreover, this algorithm also works in higher dimensions. Thank you for watching.